Swayam Prabha. Digital India. Educated India.
We shall continue with the theory of concentrating collectors. Now, we have expressed the solar radiation received by the aperture of a focusing or tracking collector, tracked in different modes, and we are also able to evaluate the tilt factor at any instant r b or for the day. Of course, for the monthly average day, as we have done for flat plate collectors or fixed slopes surfaces, R b bar m for simplicity is nothing but R b bar evaluate with delta equal to delta mean, where delta mean is the recommended mean declination for each month. So, the formula are known and there are analytical expressions for mode 1 and 4 and 5, and modes 2 and 3 are not analytically integrable. So, one may have to go for a numerical integration, whether I b under terrestrial conditions is used or even under extraterrestrial conditions. Now, the question comes, we have a parabola and with an aperture area A focused onto a receiver of area projected A r, and the geometric concentration ratio is defined as A upon A r. Now, can I have or can we have C r 10, maybe yes, 100, yes, 1000, question mark, 10,000, or is there a limit? Let me go to the next page. Is there a limit on C r? One, theoretical limit. Second thing may be practical, arising due to manufacturing. Like for example, how perfect is the reflector, how perfect is the refractor, how perfect is the optics, and though we do not aim at the 100% efficiency from the thermal point of view, will all the radiation that is passing through the aperture gets reflected and goes exactly onto the receiver, and depending upon the tracking mode. So, practically we may have, if you take the plane of the receiver, my distribution will not be a perfect rectangle like this, but it may be something like this, going much bit beyond the receiver, and technically I may have to integrate from infinity minus to plus infinity, whereas this may be of minus w by 2 to plus w by 2, and intensity also may not be uniform. This is one aspect. And regarding the reflected rays, whenever we are showing it as sort of a cross section, so this is the small receiver, classroom type, and this is the reflector coming over here. Now, if I make it a somewhat two-dimensional view, this may be the reflector and the tube may be here. So, depending upon the tracking mode, my reflected rays may go to east or west or north and south, may not exactly fall on the receiver tube. So, all that reflected radiation may not be captured by the receiver. So, effectively the concentration ratio could be different, but even if we talk about only the theoretical possible maximum concentration ratio, this has an upper limit depending upon whether it is circular concentration or linear. So, if you have a parabolic system like we have drawn now, the attempt is to focus on to a line. So, this is a sort of linear concentrator. The other way around is, if you have a paraboloidal dish, this will try to focus onto a circular area. So, technically this can be a point, this can be a line, or is it possible? So, which we shall show the possible maximum. Let this big circle be the sun of radius r at a distance of capital R from the aperture area, and at the same distance receiver also, making the half angle theta s. or 27 minutes. For a perfect concentrator, so this is the sun of radius r at a distance from the earth of capital R, and the angle subtended is 0.32 degrees onto the aperture area of AR, and AR is the receiver area. You do not have to worry that this should be before or after, it is only symbolic representation that shows AA is not equal to AR, AR is a smaller thing. The issue is, if we consider a circular concentrator, can I make AR 0 almost, making the concentration ratio infinity. So, the radiation emitted by the sun reaching the the receiver will be A r square upon r square times sigma T s to the power 4. R is the radius of the sun and capital R is the distance, sigma is the Stefan Boltzmann constant and T s is the effective temperature of the sun. A perfect receiver radiates, perfect receiver emits area A r into T r to the power 4 times the Stefan Boltzmann constant sigma. Here you may be wondering, we are not really worried about the reflectivity etc. This is the radiation intercepted by the aperture, the same thing will reach the maximum to the receiver. Now, a fraction of this will go from the receiver to the sun, because receiver is small and the sun is big. A r T r to the power 4 into sigma, of course, multiplied by the fraction E r s. So, this is of the emitted energy at a temperature of T r by the receiver, a fraction E r s will go back to the sun. Now, T r and T s, if T r equal to T s, that means in principle if the receiver reaches the sun's temperature, my Q S r should be equal to Q r s. Since there is no more temperature change between T r and T s, the emitted radiation should be equal to the radiation received from the sun. So, that gives us A by A r equal to r square by r square times E r s. Now, maximum value, we are estimating the theoretical maximum. So, I can assume this of E r s equal to 1. So, A by A r max equal to r square by r square equal to 1 by sin squared theta s. So, if theta s equal to 0.27 degrees, maximum possible concentration will be 212. That you put in the value of theta s, you will get 212. This is for a circular concentrator. So, a similar procedure for concentration, circular concentrators. Max which goes to 45,000. Okay. I will just check these values in the next class. Check. Because I think somewhere this linear and circular concentrators, they are confusing. I will just check up these numbers. Now, we will go to thermal performance. This is of course similar to flat plate collectors that we have done. And we need to obtain, however, appropriate F dash the collector efficiency factor, F R the heat removal factor, and U L the overall loss coefficient and optical parameters. Compared to a flat plate collector, if you have a concentrating reflector, there will be a reflectivity of the concentrating after the aperture. Then the receiver tube may be having a glass cover to reduce emitted and convective losses. So, this will have a tau, there will be an alpha, and there will be a rho reflectivity of the surface. Instead of just tau into alpha, we have got a reflectivity of the reflector or refractive index in the case of a refractor, and the transmittance of the outer glass cover surrounding the tube, and the absorptivity alpha. There is another additional parameter, gamma, the interceptance factor. This arises owing to all the reflected radiation may not reach the receiver due to imperfect tracking or geometric faults and non-specular reflection. What we mean is this imperfect tracking includes my tracking not being 2 axis all the time. If you are having a single axis tracking like the first mode, all the time the reflected radiation may not be within the length of the receiver tube, but many times it is argued that if you have you will not talk about a single collector, but a large number of concentrators one after the other. So, the tube is long enough so that the reflected radiation will reach the tube somewhere or the other, maybe that of the adjacent collector. Nevertheless, a part of it may be lit and part of it may not be lit. And depending upon your manufacturing technique, the mirror over here may not be perfect parabola. So, consequently, there will be some undulations because it is a large surface. So, all the reflected radiation may not be striking the receiver. Then position of the receiver itself, there may be imperfection, but most of it is due to the tracking not being perfect and this manufacturing large or reflecting surface may not be following exactly the parabola that optics requires. So, you may define that gamma, the interceptance fraction factor, is the fraction of the specularly reflected radiation intercepted by the receiver tube. So, please note it should be specular and it should be intercepted by the receiver, right. Non-specular will not reach the receiver, at least we cannot assure, and either because of imperfect specular reflection or imperfect position of the receiver, all the radiation reflected from the mirror may not reach the receiver. So, schematically you can show something like this. If this is the distribution of the intensity on the receiver plane with a finite width of minus w to plus w, and this may be going, as I said, to infinity on both sides, no matter how small it is. My interceptance factor gamma will be this may be the point A and this may be the point B, A to B I W may be the coordinate d w. So, let me put it this way, this is w upon I w d w minus infinity to plus infinity. The figure looks like A B and alpha, but they should be infinity infinity. Okay. So, this is the radiation intercepted by the receiver, and this is the radiation that technically got reflected up to including infinity, and if I find out the ratio, I will have the interceptance factor. Now, some clarification is required. Instead of that, if I have got some L as the receiver width, we may deliberately choose L less than what is needed to capture, to receive reflected radiation. Because if you see the type of distribution that we are having over here, 90% of it may be in this. So, if I add this much and this much, I will be having a larger area for the heat losses to take place, though the absorbed or reflected radiation is relatively a small portion. So, we may deliberately truncate the receiver width to a certain value. If rho is the reflectivity of the mirror, and tau alpha the transmittance absorptance product for the receiver gas tube system, and gamma is the interceptance factor. So, you have a total rho, tau, alpha, gamma effective is the sort of optical efficiency. Like S equal to IIT tau alpha for flat plate collectors, we may have S is equal to IT AA times rho tau alpha gamma for the concentrators. Of course, if you do not have a glass cover, then this tau will be equal to 1. Then the overall loss coefficient should be comprising of a wind loss coefficient from the receiver plus a radiative loss coefficient from the receiver plus a U conductance. This is due to support structure. For the receiver tube. Because like we have been showing schematically, the receiver tube will not be just hanging in air, and it has to be something like there may have to be supports with respect to the receiver or this reflector or a frame. With that, they may act like some sort of fins added to the receiver tube, and hence there may be loss. So, my overall loss coefficient will comprise of the wind loss coefficient, a radiative loss coefficient, and the conduction loss due to the support structure. And this is, of course, we can express the radiative heat transfer coefficient in terms of 4 sigma epsilon some T bar to the power 4, where as we have already defined, it is a average temperature of the receiver T r and the surrounding ambient temperatures T a in terms of the fourth powers. The heat flux in a concentrating system is higher. The heat transfer resistance from the outer surface of the receiving tube to the fluid should include the tube wall. If you recall, in our flat plate analysis, that T b minus T f has been expressed only in terms of heat transfer resistance inside, and the bond conductance or the resistance due to bond here, but the thermal conductivity of the material or the pipe has not been included, resistance due to the material has not been included. But now my fluxes are larger, which calls for including the tube resistance also. So, now we can write down a U naught which you know already. I will tell after writing down this expression. This is the resistance between the receiver and the ambient. So, this overall thing is the resistance between the fluid in the tube and the ambient. That comprises of the convective resistance inside the tube and the conduction resistance in the material of the tube of thermal conductivity K. This is what we have not included in FPC, not in FPC. Okay. So, this is what we have got, the resistance and 1 upon UL. So, basically it is the resistance from the fluid to the ambient, and this is the resistance from the receiver tube to the ambient. In fact, F dashed we have defined as 1 upon UL upon 1 upon U naught, right. So, that will be useful in calculating your collector efficiency factor also. So, if we try to make a thermal analysis for the linear concentrator, so for ease of representation I will show it horizontally. The reflector, here is the tube and maybe a glass cover or outer end in the tube simply. And if I see it here, the fluid is flowing through the, if that is the thickness of the pipe, and the temperature Tp or Tr in this case, and then there is the cover temperature Tc, and if I consider a length dx, the fluid enters at a temperature of Tf and leaves at Tf plus dTf. This is exactly similar to the what we had done for flat plate collectors. This is 1, this is 2. So, there is a glass cover. One is the absorber tube, and 2 is the glass cover. Let the width of this be W. We may have a length L perpendicular to the plane of the paper. Okay. So, now we have a reflector of width W, length perpendicular to the plane of the paper L, through which a fluid is flowing across an elemental length of dx. The temperature of the fluid increases from Tf to Tf plus dTf, and the receiver tube is at Tr or Tp in your flat plate terminology, and the outer cover is at a T cover of Tc. And with respect to the axis, and this is some sort of an angle phi. So, this indicates how big is the parabola. I mean, the parabola technically can go on up to any extent. So, now if you have, let Q u dashed be the useful energy gain per unit length of the collector. Okay. So, that perpendicular to the plane of the paper L, 1 unit length we are considering. This Q u dashed will be A A times S by L minus A R U L by L into T R minus T A. So, this A will be A W will be there, into L will be there, W will be there, L will be there, or accordingly appropriately that is included in this. This is in fact, if L is not there, it would have been the total energy gain based upon the area, absorbed energy and the loss based upon the receiver area. So, A can be considered as unshaded aperture area at times. For more accuracy, what we do is we consider that the receiver tube may cast a shadow on the aperture plane or obstruct the solar radiation entering through the aperture. There is no shadow because aperture plane is only an imaginary line, there is no physical plane present over there. AR is the receiver area, okay. It is just like the energy balance we have done, and Q u dashed can be written in terms of the local fluid temperature T f and T r. So, Q u dashed will be A r by L into T r minus T f by D naught by H f I d I plus D naught by 2 k log D naught by d I. You will find that this is the temperature difference available between the receiver and the fluid of area A r per unit length, and this is the resistance for the convection inside the tube, and this is the resistance due to the wall of the tube. So, Q u dashed, as we commonly expressed as f dashed times A area of the aperture per unit area times absorbed energy minus A by A r times U L times T f minus T A. This should be A r by A A, otherwise it will lose more heat. So, now if you compare these equations, f dashed will be given by 1 upon U L by 1 upon U L plus D naught